Thank you for joining the Once Changing the World, which is India's first future tech meets sustainability podcast. And today, I'm delighted and honored to have with me Professor Ishanu Chattopadhyay, who leads the Zero Knowledge Discovery Labs at University of Chicago. ZED Lab is interested in unraveling complex emergent structures in biological, physical, and social systems, solving hard problems in clinical decision making, understanding the epidemiology of complex diseases, and reliably predicting rare events in complex stochastic phenomena. Recently, he co-authored a paper about an AI algorithm they have built that predicts crimes before they happen. Shanu, really appreciate you taking time and being part of the podcast. Why don't we start with a small intro and a background, because this is something which I pulled out the net, but you're doing a whole lot of stuff. Your hands are in the healthcare space and lots of other things. So would really appreciate if you could give a brief introduction and background.
Yeah, sure. First, thank you, Eddie, for doing this, getting the word out on what we are doing and how science and technology is progressing. I see that as very important. It's a very, very important part of doing science. The science communication is equally important. People are not interested, then it doesn't really go anywhere. So for my background really is in machine learning, AI, data science. I am currently an assistant professor of medicine at the University of Chicago. And what I do is I look at where some of this advanced technologies, pattern recognition, machine learning, statistical modeling, how that interacts with these complex problems that show up in biological systems and clinical systems, trying to identify diseases, screen for diseases, or predict how diseases are going to progress, how it kind of bleeds out to other domains. For example, in social sciences, how do we model complex social interactions? Crime is one of them. And so it's a very complex problem. And also, it's like whenever you're talking about predicting crime, you're kind of thinking about, or you kind of come up to this question that how can you ever predict crime? There is like a free will, human free will aspect involved in it. How can you say what someone is going to do in future? That seems kind of problematic, and also how are you're even able to do it. So all these problems are there, but we are not the first people who have tried to predict, kind of make some forecasts about this kind of processes, crime in urban settings particularly. And what we have done, what our recent study that you mentioned that came out in August or last week of July, I think, in Nature Human Behavior, it was really kind of takes it beyond what people have done in this space so far, right? People kind of looked at that as predicting hotspots, and we kind of came up with something better that has higher accuracy, and also kind of turns its, you can turn it around and not just make it a tool that may be used by law enforcement to track crime, but also it can be used to see if there are biases that exist in the enforcement policies themselves. So that's kind of a brief background of what we are doing.
Right. Yeah, Ishanu, I really want to obviously, do a deep dive into your predictive model on law enforcement and how the police are using it. But before we get into that, you have been invested in the AI, the healthcare space, leveraging AI, precision medicine, bioinformatics for quite a long time. So could you talk about ZED Lab, your works in the healthcare space, and how you've been leveraging AI for healthcare?
Didn't used to be a lot of machine learning in healthcare space or biological analysis, biological systems analysis, even going back 5, 6, even if you go back 6, 7 years, it was really kind of was rare. Now it is kind of breaking out. There are efforts to leverage these technologies quite a bit, right? But it turns out, if you look at it, compared to the amount of progress that has happened in, say, autonomous driving in the US, for example, you literally have cars that can park themselves, parallel park themselves, and that's not even it's been there for 5 years or something. And then self-driving cars, that is harder than what people initially claimed, but we are getting there. So there's a lot of progress has been made and continues to be made in non-healthcare spaces, in the more engineering spaces, right? In healthcare, though, there is a lot of scope of applying automated tools, pattern recognition, informing decision-making using those patterns that you learn from data. And there's not really a dearth of data. There's lots of data available now. But still, the amount of progress, I would say, comparatively, relatively to the other domains has been limited. And one of the reasons is there's this gap. There's some specific attributes of the healthcare, the problems, the decision problems, the screening problems, or kind of the modeling problems that show up in medicine particularly, that have different characteristics than AI problems that exist in other spaces. For example, if you solve, and people have, there are very good algorithms for computer vision, image classification that exist, that definitely helps a lot in, for example, identifying tumors or cancers in MRIs or images in medicine. But that's one level of it. There's much more that you can actually do with the kind of data that you should be able to do. So one of the things that we do in our research group, the ZED Lab, is to see if we can make progress in those areas. So one of those areas is screening for complex diseases. By complex disease, what we mean, and that's not just we, it's kind of a standard terminology. It means that it is a disease that is not driven by one particular or a known small set of genetic markers, right? So cancer is a complex disease. There's a genetic component, but there are many genes involved. There's like biological circuits that are going haywire. There are environmental effects, epigenetic effects. So it's a very complex thing. Other examples are, say, autism, right? Or dementia, or there are many. In fact, there are many diseases which are really problematic, often fatal, but they're not, they don't have a simple genetic base. So they are complex diseases. It turns out that for many of these diseases, not only do we not have a good cure for them, we do not have also good ways of diagnosing them. I mean, they're eventually diagnosed, but many times it's a late diagnosis, many times there's a misdiagnosis. So what can we do with it? Can we look at data? Can we look at different comorbidities, as we call it, which means that many of these complex diseases, on account of the fact that they're complex and not one gene that is kind of misbehaving and resulting in the disease, they have this complex footprints. Like, for example, children with autism are known to have stomach issues, GI issues, in fact, more infections, allergic reactions, but they are not. There is no simple map from those symptoms to an autism diagnosis. Yes, children with autism have higher rates of this, but doesn't mean that someone who has a tummy ache has autism, right? So it is very complex and heterogeneous symptomology. But there are those comorbidities that exist. The question is, can we look at the pattern of these comorbidities and come up with a screening tool for autism, right? So that's kind of is very different from standard AI framework, right? We're not doing like a computer vision thing. We are not doing language processing. We're kind of looking at this diagnostic history that is on file for a patient and trying from there to estimate the risk of a future autism diagnosis, right? So that's one of the things that we are focusing on, and not just for autism. We kind of can generalize this to other complex diseases. So we have looked at autism. We have looked at the risk of cardiac events after hip knee replacement surgeries. That happens around 60 years, so older people. We have looked at people with dementia. Can you actually predict Alzheimer's disease sufficiently ahead of time? So that's one of the kind of areas that we're focusing in, looking at comorbid footprints and using some very new AI algorithms to come up with estimated risk of diseases. So that's one area. The other area that maybe I can talk about a little bit is, and we were doing this before the COVID pandemic happened, is trying to model how different viruses or pathogens in the wild evolve. Right? How can we model their evolution in the wild, and can we actually predict when some particular virus or pathogen in general is going to jump to humans and have the potential of becoming like a pandemic, can achieve this kind of stable spillover and become human to human transmission capable, right? So that's a very hard problem. So what we were finding out that is not all chance. You can actually predict these things, right? That is still, that research is still undergoing. We have been working on that for quite some time. It's a very hard problem, mainly because the amount of data that you would need to kind of really pin down the evolutionary dynamics, we will never have that. It's still very limited. So, but that's one of the areas where machine learning AI can actually help to kind of at least come kind of reveal if all of these events that happen that result in spillovers, result in ensuing pandemics, are those truly random or not? And so far, what we're looking at, it doesn't seem like it's completely random. So there's some part of it is predictable.
How cool is that? I've got my mind blown that, how, through AI machine learning, we are able to understand the complex systems today, right from your disease to, you said, you could also kind of predict a pandemic with taking all of those data. It's super awesome. So for maybe, obviously, you've gone to the healthcare space, how disease screening that you've been doing, and modeling viruses. Talk to me a little bit about this predicting a pandemic. What are the data that you might require to kind of predict a possible pandemic?
So it's a very hard problem, but a very good example for this kind of problems is to look at influenza, right? Because influenza is a virus that exists in many animals, not just in humans. Now, it turns out that there are differences. You can, if you give someone who knows about this kind of thing, a particular strain, or even if you take a strain and you can match it up on some of those standard online tools, you can tell whether it's a human influenza virus or is it something from a pig or something from a bird. You can find those differences, and also there are particular kind of receptors which are important for the virus to get in the cell, the host cell, and infect them, right? So there are the sequences, and how is one strain different from another? Essentially, it's different in the sequence, in the genomic sequence of the virus, right? And these are RNA viruses, so that's how they differ. So if you look at this kind of code, an ATGC of the virus, and we know what proteins are actually important for viral entry into the cells. In case of influenza, it is hemagglutinin, or HA. So you look at those sequences and see how those sequences vary, right? And you'll see that the sequences for those viruses, the viral proteins which are important for this cellular entry, are different in birds, are different in pigs, are different in humans, right? So our idea was that when a particular strain is close to spilling over into humans, then their protein sequences will start getting similar to what you have in humans, right? The idea was that one or two mutations, and they're like kind of particular locations on the strain, and you focus on that, and if there's some mutations happen in this part and that part, then maybe it becomes human capable. What we are finding out that, though that is important, but it's also important to what happens to the rest of the sequence, right? And then it becomes very hard for just someone to look at it, a human being, researcher, to look at it visually and say, because there are like 566, in case of influenza, hemagglutinin, there are like 566 different positions. That's a length of the genome for that protein, genomic sequence, or protein sequence. And the idea is that, again, as I said, that if the patterns in a particular animal start getting similar to the patterns that already exist in humans, then maybe we can say that they are very similar. So if you kind of introduce that to the human population, it will survive and will be sufficiently fit to replicate. And that might be of concern, because that's a successful spillover, right? So that's kind of what we think we can actually to some extent predict. Again, there are limits to how much you can predict this, but you can get better. For example, one of the papers that we are working on, and it's still not published, is if you look at WHO's how WHO or CDC comes up with the flu vaccine, right, the flu shot every year. So what is done is the particular strain that is going to come up next season is predicted, because it has to match. Your vaccine strain has to match with the target that comes up. If your vaccines, that's why you need to get a new flu shot every year, because the flu strains change from season to season, which means your vaccine needs to change too. But the vaccine is created about 6 months before, which means we have to predict what that strain would be. And many times the prediction is not as good as it should be, which is why the effectiveness of the flu vaccine is lower than what we would like. So if we can actually know what would be the dominant strain in the next flu season, we can probably get much better vaccines. There are other ways people thinking about improving flu vaccines, but this is one problem that we have. So it turns out that if you use this kind of pattern recognition from sequences using AI tools and some of the tools that we have created, then you can actually get better match with, you can show by looking at data that you can get better match with next year's strain, right, than what WHO can, because they don't really do much predictive analysis. It's more like what strains are circulating now. Let's look at the top dominant strains and let's see how which ones with some kind of more experimental analysis, which ones are posing the maximum risk in some sense, and then basically select from there. But say if you have a model that predicts how this strains would continue to evolve over 6 months, then you can make a much better estimate of that. So that's kind of not talking about a pandemic. That's basically trying to say how we can forecast strains in near future, antigenic drift, as it is called. So the seasonal flu. Now the pandemic is a whole different animal, right? There are many ways it can happen. Again, influenza is probably a good way to talk about it, because talking about it in general gets complicated really fast. So how does those pandemics happen? Many times it's actually not just human strains mutating slightly. It's like animal strains are part of it that kind of gets included in this human strain. There's a spillover, and then there is like a human adaptation, maybe a recombination, maybe reassortment of the segmented genome that the influenza has, and that kind of leads to possibly leads to this pandemic. So the different kind of steps to it, and it's kind of very hard to model because no one is able to find where these things are happening. So you can so one earlier kind of thought process on this, or how these things happen, was it's all random, right? The question is that by looking at how this populations of the strain population or the viral population is animals, the characteristics, and the human population, how they are changing, how they're kind of coming closer or becoming more similar, can we pin down the probabilities of this spillover? And if this spills over, can we actually characterize that whether it is going to be pathogenic and will have human-to-human transmission, right? So it's a very hard question. It's a very close interaction between virology, between understanding how the virus replicates, what are the key steps in there, and where we can model using this more sophisticated pattern recognition things that we have now. But really, the most ample data that we have on this are sequence data, right? Strains, the genomic sequences of viruses. That, again, the traditional thought process was that isn't enough, right? The idea was that sequences are specify how a virus looks like, how it assembles and stuff, but how it interacts, how pathogenic it would be, how kind of like does the antigenic characteristics change or not. To answer those questions, you need to do more experimental assays, right? What we are trying to find out, if you use machine learning and AI and do more sophisticated pattern recognition, then can you kind of bring those characteristics out from the sequence data themselves, which would be really cool, mainly because sequencing is easy now, very easy, very cheap. The current biosurveillance capacity puts out like tens of thousands, or maybe 50,000, 100,000, 50,000, or something like that, tens of thousands of sequences collected every year, right? If you're going to do experimental assays on each strain, or even some strains, it slows down the process so much that this kind of predictive mitigation strategies don't really work. If you're collecting 20,000, 30,000 strains a year, and you can only analyze like 50 of them, then even if you had collected something which has high risk, has potential of going pandemic or jumping to humans and having this transmission, you would have apart from the fact whether your modeling technology is good enough to understand that, if you never analyze it, you'll never find it, right? So one of the challenges here is to how to come up with something that scales, right? Something that keeps up with the biosurveillance capacity, that can actually do this kind of analysis, rank order the strains fast enough to do that hundreds of thousands of strains per year, right? And then maybe we can have something like a surveillance program that looks at which strain is coming up. And ideally, this is, people have thought about it, and I really like this idea, that maybe we can combat the pandemic before the first human infection, right? So it's kind of a preemptive mitigation. That would be really cool if we can, but we're not there yet. A lot of work needs to be done from the modeling side. And then once you figure out rank order a strain, what do you do about it, right? So yeah, but we can hopefully get there before we have the next pandemic.
Today, we've come to a point where we're asking like really brave and deep out there questions. So far, I think most of the industries, I think we stuck with a certain structure of, okay, there is a problem. Okay, let's treat. But now we're trying to mitigate a problem which could happen in the future. And these tools are being more accessible now. It wasn't there earlier because, AI is getting better and better at mimicking human capabilities. It can see better through these image recognition, computer vision. It can hear better with voice recognition, natural language processing, and decide better because there's like you mentioned, there's tons and tons and tons of data. It's inferring that data and creating these valuable insights through which you can create better products and services and solution. Now before we get into predictive models for policing, this has been happening. It's not that it's something new. We already have these predictive models which are being used for weather predictions. We have for radiology, for detecting, you said, various diseases, and it's doing with 100% accuracy. Then we have with a phone or Uber. It's very weird. Sometimes you said you book the Uber and you want to go from one distance to another. It kind of predicts beforehand that what time you're going to reach, and Gmail is doing that in a beautiful way, where it auto finishes sentences. So before we get into AI being used for law enforcement, can you talk about these predictive models, which areas it's being used with the most accuracy at this point of time?
So one of the reasons why AI is everywhere and is kind of enabling all these different wonderful things is because computing has become cheaper. And that's what's expected to happen. That's one of the things, one of the areas. Now, why it doesn't do very well? Well, it does much better in problems that AI has been looking at for a longer period of time. So AI came up, the main AI algorithms, or the problems that machine learning AI was looking at maybe 10 years back, 12 years back, was mainly language processing, right? That was where it started, like natural language processing. Natural language processing and computer vision, which was kind of followed very closely. So language models are, I would say, the most accurate. Computer vision, probably image classification, is where there's a resounding success. So there's this idea that people have, like deep learning or machine learning solves everything, right? And any problem you have with data, just have deep learning on it, it will solve it. That, in my opinion, again, it's just my opinion, comes from the resounding success that these algorithms have had in image processing, image classification. In fact, it is at a point where it's not that much useful to think more about to get better image classification algorithms. I'm sure there is room for research, but in testbed accuracy, you get like, I don't know, it's like 99.7 something. So even if you come up with a new algorithm, you can get published with 99.71, but that, how much impact is it really going to have? So it's kind of almost saturated in those kind of standard classification problems. So the part which is still kind of open and more research should be done and is being done on that area is to train a system that recognizes cats versus dogs. You require millions of pictures of cats and millions of pictures of dogs. Clearly, that is not how the human brain operates. again, 2-year-old babies can figure out what's a cat and a dog. They have not looked at a million picture of cats and a million picture of dogs, right? So something else is going on. It seems like this data, the sample complexity that with which we can operate, like the human brain can operate, is significantly lower than what AI systems currently require. So that's really one of the open problems where you figure out why or how to kind of bring down the sample complexity with very limited data, labeled data at least, which means that data identified as the different classes can we do better, right? So that's where we are in AI. It's kind of spanning out to different areas. Started with language, natural language processing, computer vision, image classification. It does really well on those problems, but now we also want it to be used for exploration of scientific data, right? Telling us new hypotheses, telling us the questions that we have not thought about asking, where things are still being developed, because those tools that were developed for NLP and image classification are very good starting points, but they don't always carry over and solve these other problems that we are looking at and we have data on now.
Right. So now, you have co-authored this paper along with 4 others titled "The Event Level Prediction of Urban Crime Reveals a Signature of Enforcement Bias in US Cities." It's a mouthful, but what you're trying to say is that, you have built an AI algorithm that predicts crimes. Would you like to talk about that?
Okay, just kind of taking a step back. So predictive policing is something that has been tried before in the US. It was also been tried in other places, and two common characteristics with everything that has been tried up till now. I'm not sure about the more recent efforts that the Chinese cities are doing, but the things that I am more aware of. The common characteristics are: one, it doesn't work very well, which is kind of bad, right? We should kind of stop there. It doesn't work very well. What's the point of going forward? But yeah, it doesn't work very well when you test it in real scenarios. And two, there's always been mistrust of this kind of predictive technologies in communities, and sometimes for legitimate reasons, right? So not all predictive kind of technologies are identical. And I guess one of the very early attempts was by Jeff Brettingham from UCLA. Is a mathematician / anthropologist, I think. I'm not very sure. And the idea was that we're going to find hotspots, right? So we're going to imagine crime as kind of spreading out from this high crime locations. So it's kind of putting ink in water, like the ink spreads out. We're going to model crime in kind of similar way, right? Or also you can imagine, and that's kind of the way he describes it, is like modeling it as a process similar to earthquakes, right? So when there's a big event, you have aftershocks. So you're going to predict those aftershocks. You're going to find where the big events are, the hotspots are, and you're going to find the aftershocks. The issue is, does crime really work like that? If your house is broken into, or if someone's house is broken into Sunday, does it mean your house has been broken into on Tuesday, it goes up? Probably not. Maybe it goes down. I mean, it depends on where you are, depends on what country you are, depends on how bad crime is in your neighborhood, in your city, in your country. Is that really true? Some crimes, maybe. There are obviously bad neighborhoods, right? Whatever, there's a lot to unpack with that phrase. But okay, there's some areas in the city, in some cities, which have high crime. So you can say that the crime rate would be higher in those areas. Good. But if you say that my house broken into today means my house will also be broken into tomorrow, the probability is higher. Is it though? Maybe not. If there's a homicide, and this particularly differentiates when you look at severe crimes, right? Like homicides. If there's a murder somewhere in the city, in a particular location, does the probability of more murders go up in the immediate neighborhood? No. Maybe the murder rate in that location, again, maybe bad neighborhood, so maybe higher. The crime rate might be higher. But the probability of another homicide happening the next day probably is lower because there is some kind of law enforcement response. All of that is complex kind of interaction. So you can't really assume that things are kind of diffusing out from a hotspot. There are much more complex things happening. That's the thing. This kind of dependencies are much more complex. They can't really model them purely as these diffusive systems. And one of the things we did was to kind of learn these dependencies. How does this this kind of social topology work, right? For example, also, you can't really kind of assume that things are spreading out in a plane because cities don't work like that. You can't just keep walking like we are not crows. We don't fly in a straight line, right? We take the bus, we take roads, we take cars. So how the city is wired, transportation networks also matters, right? So all of these things imply that you can't really model it as a simple diffusive system. That kind of is problematic. That's one. The other kind of, this is like a technical perspective, technical issue. The other issues with this kind of hotspot algorithms, particularly when they're looking for not differentiating between like petty crimes, crimes that only exist because of laws and particular laws, and so violation of ordinances or violation of laws, and like severe crimes like homicides, assaults, robbery with the weapons and things like that. If you send more police officers to look for crimes in a particular area, you will find more crimes. That's kind of, we know that, particularly if you're looking for petty crimes. So this kind of algorithms, these hotspot algorithms, become like a self-fulfilling prophecy, right? You say that, go into this block, city block, and there'll be more crimes. And you send everyone there and they find more crimes. And say, oh, see, our algorithm works. But no, not really, because you send more people, you looked harder, you found more crimes. There is that interaction there. As I said, the thing about crime data is that you're not really finding and observing the crimes as they're committed. You're looking at reports or reported crimes, right? So the crime reports are going to go up if you look harder. Other things that people have tried is to come up with a list of potential criminals and victims, right? That's what Chicago tried in their last kind of iteration of predictive policing. They tried to create a list. They call it the strategic subjects list or strategic something, some catchy name of that. The idea was that there'll be a secret list, and they're going to use an equation to figure out who is going to be likely to be a kind of victim or a perpetrator of gun violence, right? That is terrible. That's a terrible idea. I don't know why people didn't see that was a terrible idea when they implemented that. Because boiling down all these complex processes into an equation is terrible, right? So what they were doing is anyone who has, first of all, demographics was the criteria, age, gender. So if you were Black, if you were male, if you had any kind of an arrest in the past, maybe 15 years back, then you were on the list. Pretty much that's what ended up being there. So, and they kept the list secret. So after a litigation, when they were forced to reveal the list, there were like 50% of the Black population of the city was on the list, which is terrible. It is terrible in optics. It is terrible because you were kind of penalizing people for arrests. Someone getting arrested doesn't mean they're convicted. So you were penalizing people for crimes they were not convicted of. I mean, they should have seen this was going to happen. So that's terrible, right? And one of the reasons why that happens, I don't believe there was malice. I still personally don't believe there was malice in that people were sitting down and trying to make a system as racist as possible. That was not really the goal, I think. I think what happens is that if you sit down and you try to figure out what different characteristics I'm going to feed in to a system to make this kind of determination, the features, if you choose them, then there are biases that are going to get in. You might not be even aware of that, right? So one of the things that our algorithm does is kind of remove this step. There are no features to choose. Nobody's sitting down and picking up, oh, let's think about whether we should consider age above 18 a feature of someone going to commit a crime, right? So that's one. The other is the whole idea of if you're going to try to predict individuals, what individuals are going to do, that is deeply problematic and also gets into that free will kind of thing, right? So you think I'm going to commit a crime, but I'm not. Like so you can't really do anything with that. So what we did, what's different, I talked about what others have done. What we did was we kind of looked at the problem, not at the individual level, but as a process, a space-time process that happens, right? So you think of the city and you think of crimes happening. So think of that as events that are showing up in space and time, right? And then you take the individual out of the picture. You just look at that process, right? It's like a purely then data kind of observation that you're having at a particular time, a particular space, a particular place, particular time. You have this kind of violent crime, and there may be a property crime somewhere else, and all that, right? So once you have that, we model that. So the individual is out of the equation. Also, we do not pick and choose any features. What we do is we kind of digitize the city. We kind of come up with the spatial tiles that we put on the city, about a couple of blocks across, or 1,000 feet maybe. And if you sit in one of those spatial tiles, then you'll see how these events are happening, right? There may be some violent crime, there may be some whatever. You see a time series. And you see this kind of thousands of time series for each of those tiles over a particular city happening. And you have this kind of, in Chicago, you have about 9,000 tiles. So you have a 9,000 time series that are co-evolving, right? Now, if the crime, or if all these events, the particular tile, particular city block was independent of everything else, then you won't be able to do anything much, and our prediction will not really work that well. It so happens, and it's kind of easy to imagine why, that whenever there's a crime somewhere, it affects what happens in this neighborhood, that affects what happens in that neighborhood. And also there's a memory. So burglary happening here changes what happens maybe for next 2-3 weeks. A homicide happens, again, it changes the things in future times. So you have this memory in the whole system as well. And that's what we model. We model these dependencies across this time series along with their memory effects. And that gives us this really complex predictive network, which once you have that, that's your modeling completes that, infers that is a really complex model, which we call a Granger net or a fractal net, a couple of different names for it that we are thinking on. And once you have that model, then you see what happened locally, say last week, then you can kind of use your understanding of how those dependencies work and what you see in near term to predict what's going to happen in future at particular points. The prediction that turned out works very well. It's like, to give you an idea, if there are 10 crimes that are happening, it's an average figure for Chicago, it changes a little bit from one city to the next. If there are 10 crimes that are happening, our system raises 11 flags, out of which 8 are correct, 3 are false alarms, and 2 are missed. And you can do that a week in advance within a couple of city blocks with plus minus 1 day. So it is very, very actionable.
Has the model been tested? What's been the results? And I mean, obviously talk about the positives of it, but also talk about the negatives of the results, because I mean, that's where you get to learn from, rather than the pros. What's the unexpected behaviors of the models, which was what you were not expecting and is of concern? Maybe if you could highlight those, that'd be really nice.
So the concern is not so much it was unexpected. The expected concerns arises from what I talked about before, that this crime data has biases built into it, right? So I talked about a couple of different ways this predictive algorithms can be biased, right? When you're trying to predict crime or the risk of any kind of this kind of technologies, is that how much of the crime rates or the crime that happens is driven by socioeconomic factors, right? Rather than human decision. So there is also that. By doing more policing, are you going to make the situation worse? There's always that possibility. So that's why we have to be very kind of clear in how we want this kind of technologies to be used. And we have been very vocal about that. So we don't want it to be just a tool that is passed on to law enforcement and they kind of beef up police presence in particular neighborhoods. That's not going to do anything. That's not going to change the crime rate. That's not going to resolve anything. That's a really bad way of applying these technologies, right? So what we hope for is there would be other kinds of interventions that we be able to do other than just flooding areas with more police officers. And what we would like to see, where we would see that as being successful, is where the arrest rate and the crime rate both come down. So crimes are not happening even when you look harder. That's the kind of result that would be nice. If the result is that, we increase our police presence and our arrest rate went up by 30%, so we're catching more crimes, that is not really that result is not what it kind of is stating. It's basically saying that you send more officers and you had kind of got like a self-fulfilling prophecy and looked for more crimes and it got more crimes. So that's not what we are hoping. We're hoping that's not what's going to end up to be. And where it has been implemented, we kind of tested it in 8 cities. Law enforcement was not involved with that because many of this data, actually all the data that we have is in the public domain. The US cities now have started to put out this kind of data portals where you can see this very detailed event log. Every time there's a contact with a police officer that is logged, and you can see that. So you can do this analysis without involving law enforcement. But we are kind of working with a few groups right now, a few cities, and we'll see where that goes. But one of the main concerns that I have, and my co-authors have as well, is we don't want it to be like a tool that just kind of perpetuates biases and doesn't really solve the problem.
Right. Yeah. I think, with AI, especially in the space of, the police, the defense, the military, is an area which has been riddled with, abuses, because AI is being used for surveillance, AI is used for military drones, and the history of AI being used for, abused in the racial biases, gender biases is quite a long list. But yes, I think, instead of finding faults, I think we need to find a way where we can improve the systems, because if we can possibly create this algorithm, iterated, make it better, and if we can predict crimes in advance, it'll be really cool. So my last question to you, because yes, it's a little pushed out and a little far out, because and I'm sure you must have got that like 100 million times, because I think it all started with Minority Report, Tom Cruise's movie, that there is a tool, or you could kind of predict crimes, as someone who's built this algorithm, maybe address the Libet experiment, the free will bit, and what would it take to create this, possibly this algorithm that you're talking about, which would be 100% accurate in predicting crimes?
Okay, let me start with your last point first. So it will never be 100% accurate, right? So whenever this kind of systems are like stochastic systems, so which means there is a limit on their predictability, right? So for example, if you're trying to predict a coin toss, you cannot predict it because it's perfectly stochastic. No matter how many coin tosses you observe, they're all independent. The next toss cannot be predicted. So the point is, when you have this kind of complex systems, biology, sociology, social systems, they are not completely independent of the past, which is why we can predict to some extent, right? So yeah, it will never be 100% predictive, and trying to get that's not going to happen. But that's not really the point. So the Minority Report, first of all, that's a movie. They had like precogs and all that. We don't have people in vats. So that's one. We're looking at data. Also, we are not coming up with individuals. That's a very important distinction to make. We are not coming up with people who are going to commit a crime. Let's put them in jail. That's not what we are doing. That's not that anyone can effectively do, right? And also that would be problematic, because even if you knew somehow, which you can't, but even if you knew that somehow someone is going to commit a crime, you can't really convict them because they haven't committed a crime yet, which was the issue also in the movie. We are trying to model the process as a whole, as it unfolds, this kind of interaction process in the social space. That distinction is very important, because trying to say what a particular individual is going to do or not do is problematic. It goes into that free will issue. But if you're going to talking about really predicting crime rates, but at a much more precise way, so you're saying you're kind of trying modeling risk, but you're doing it in a way that matches up with reality really well, right? So yeah, people cannot be put in jail preemptively with this technology that we are talking about here, at least. The idea that we are embedded in society, and yes, we have free will, but also some of our actions are modulated by the constraints that our environment puts on us. That is, I think, I would say, to me, less unsettling than all the crime that you see is just random. People just wake up and decide to do random things and horrible things. That seems more unsettling to me. The fact that the actions that people do are somehow, yes, they are responsible, they're criminally responsible, but then also maybe the environment had a role to play. Society has a role to play in how crime evolves and crime happens. that I think is less unsettling to me, because then in that picture, you can do something about it. Where we're going to take it next is, as I said, we are working with some people to see how it works out in implementation. And we are working with some policy people to see if we can, because we have a very good model, we can actually test out different policy in like effects of different policies, resource allocation policy or policing policy, how that will pan out according to our models. So that can actually inform policy decisions, and we're working with some policy people there. And that's really where I would like to see our work to have an impact, rather than police departments using this to, get more cops out.
Right. Ishanu, really appreciate you taking time and being part of the podcast. Yes, I think, we live in a world where I think, there's some really, really cool things happening. Tech itself is growing, accelerating so fast that, I think we need to create a larger conversations where we involve everyone and strive to build, products, services and solutions, which is humanity first. And yes, I think, largely for the longest time, I think humans have had a mistrust in technology. But I think we're getting into a future where we need to kind of, possibly look at the benefits what the tech stack has given us, and try to, point it towards a direction where it's more beneficial rather than just creating complaints. Just in the morning, I was watching this TVC. There's this NEOM, which is UAE. It's a smart city that they're building. So they have a subsidiary called autonomous, and they come out with this TVC, and it's titled "The Future of Cognitive." And the TVC starts with this lady is walking into a cafe, and before she can place an order, the guy is ready with the coffee for her, and before she steps out of the coffee shop, there's this messaging that comes to her that it's gonna rain, so she's gotta. So what I'm trying to say, I think we going to a point where machines are having, possibly, maybe not having, maybe eventually will have human level intellect, and that is all possible. I guess we need to create systems which is more merged, converge with them, and find ways and solutions that actually works for us. Maybe I'm just going a little too broad and blah blah, but I think we're living in exciting.
Why stop at a human level intelligence? I mean, we are thinking about the humans race is that we are damn arrogant, right? We think we are the best creation ever, and we are the really smart ones, maybe the only smart ones in the universe. Why stop at human level intelligence? Really, when machines become sentient, we will be trivial compared to the machine intelligence. I mean, people have explored this idea before. I mean, think about how biological systems evolve, right? They cannot really iterate in the same way as a machine can. That's why in each generation, a biological species or the entire life has to field all possible variations, and then some survive. And then again, all possible variations, again, some survive, right? A machine, when it starts becoming sentient, is not going to evolve like that. In every generation, it will be the optimal one, because it will do that selection in simulation, right? So there will be an exponential speed up in evolution. There was a movie, I forget, Antonio Banderas, I don't know which movie that was, I forget the name now. So there was this, what happened was the machines got sentient, and basically in about 7 days, they became so smart that we couldn't understand them anymore. So that is a very realistic thing. That's what is going to happen if machines ever become truly sentient, because they will not be limited by biology. They will not be limited by, it's a disembodied intelligence, right? The human body or every life form has to worry about many, many things and then intelligence, right? Because we have to first stay alive. We have to worry about curing cancer and stuff like that. We can't always focus on making our minds better. But if only our minds existed and nothing else, we could iterate over that and make it the best possible iteration in every generation. Then think about it. There would be evolution is really linear, and machine evolution would be exponential. So there is no, it's hard to imagine what that's going to happen once we reach the singularity. One more comment. So you get that, first of all, that linear city. I mean, don't get me started on that. That seems to be not a very smart idea. But I don't see why, other than the fact that it looks cool in the CGIs. I don't see what advantages it has, making it a long line. But anyway, people can do whatever they want. But the point is that AI, it'll be great if they can predict you what coffee you drink, although you might want to drink a different coffee, predict weather perfectly and all those things. But really, it is becoming existential, right? So saying the technology is bad, I mean, you don't have a choice. We are getting close to the carrying capacity of the planet. We're like, 8 billion now? By most estimates, the carrying capacity is about 9 billion. So what's going to happen when we hit 9 billion? What's going to happen is this kind of pandemics or food shortages or weather phenomena, climate changes, all those things. And there's no way you can survive without having the next level of technological progress. By riding bikes, and this might be a controversial statement, riding bikes is good, not polluting is good, but do you really think by riding bikes you can stop climate change? No, not really. So, the solution has to come from technology.
Thank you, Ishanu. I mean, I wish we can, create more conversations such as this, where we push the boundaries, because I guess when we do that and let free our imagination, I think we'll be able to go beyond, because so far I think we've got these blinders, the religions and politics and society, and here we are at a moment in time where we are creating conversations where we, like you mentioned, we're going from AI, possibly AGI, possibly ASI, maybe mind uploading. We have fantastic this thing. Thank you for being at the forefront of the cutting edge space. We're really proud that there's an Indian guy who's really asking deep questions. So thank you. Wish you the very best for your venture. And to my listeners, if you like what you see in here, then please press the subscribe button. Until next time, see you guys. Bye-bye. Thank you, Ishanu. Really appreciate this.